All right. So Luke is going to stand here and help me with the demonstration. So I'm going to talk to you today about CAVE2, which we call a hybrid reality environment, and I'll explain that term in a moment. But first of all, a bit of history. I have to tip my hat off to Tom DeFonte and Dan Sandine, because this is really based a lot on the original work that they did in 1991 by inventing the CAVE. At the time, I was a fresh, new PhD student, and I just adored the technology. And I lived in the lab for 6 years, and I actually never left. I'm still there. And over the years, the projection technology has evolved. To become cheaper, so that we've been able to deploy, PowerPoint-type projectors with polarizers to give you stereo. But roughly around 1996 was when I was working on my PhD, finally finishing, and I was working with General Motors intensely on cave-to-cave collaboration, and that's when I really became interested in distance collaboration environments. And so in 2000, I started thinking, well, can we put together an environment that allows you to look at content at very high resolution, both 2D and 3D? So we constructed the system on the bottom left that had, at the time, plasma screens for multi-site video conferencing, had a geo-wall projection-based display for stereoscopic viewing, and then on the far right, at the corner here, was a small 2x2 tiling of LCDs. And what we'd hope to achieve, and finally are able to achieve today, is basically an environment where we are beginning to able to sort of merge a lot of these properties together into what we call the Cyber Commons, because it was funded by the Optiputer project, so that people can actually work together, co-located as well as distributed. In the scenario that you're seeing on the bottom right, the users are able to wirelessly push their laptop screens directly onto the walls. If they have a document that they're working with, they can drag and drop it to the little icon, and it will appear on the wall. They can drag any of the documents on the wall to little icons and ship a copy to a remote site where the collaborators on the other side can also look at this. And actually, much of what we're seeing here is actually not being rendered locally. This is sort of, again, the separation between geometry and pixels. We're actually streaming pixels over long distance onto the screens. So my desire then in building the CAVE, the new CAVE system, was to try and merge the bottom right with the top left. The top left was sort of the best in class for virtual reality, and the bottom right was the best in class for high resolution display of content. And so in October of this year, we unveiled for the first time CAVE2, and here's a little animation showing its structure. Basically, it's a full 320-degree cylinder, LCD panels, flat panel, capable of passive stereo. We're not pictured here is a optical tracking system for viewer center perspective, and also a 20-speaker ambisonic surround sound system. Later on, when we do the actual live tour at EVL, you're going to get to see all these little parts moving. But before I get there, I just want to explain how we're doing some of the stereo and what are some of the issues we ran into. So, so basically, we're using passive polarization. This is a kind of technology you can now buy from Best Buy, right, from LG, where essentially the pixels are mediated by an interleaving of polarizers to give you left and right eye stereo. Now, these are actually great for essentially on-axis viewing, and also great for horizontal viewing. But the moment you start moving your head up and down, ghosting starts to occur. Now, that's a problem in the CAVE, because in virtual reality, we tend to like to walk close to objects. And then if you have a structure that's 8 feet tall, you're becoming very, very off-axis with the top display, such as what you're seeing here. And so Cal IT2 had actually done some work to try and resolve some of these issues, and they had developed, Tom had developed something called NextCave, which is basically tiling the LCDs but tilting the top ones down to try and accommodate for this off-axis problem. And so we decided that we want to try and see if we can come up with a different solution to that that didn't require us to tilt the displays. So these are actually one of the early prototype sketches of the various configurations that we went through, all of which are essentially tilted displays because we couldn't figure a good solution at the time. Our favorite, two favorite ones is the TIE Fighter and the Tootsie Roll. If we had to build one, we'd probably build a TIE Fighter because we're like Star Wars fans. But what we decided to do was, and speaking with display manufacturers and Mechdyne, which is one of the companies that builds the caves, they said that one of the concerns with a structure like this is that if you had these tilted tiles, you couldn't really build a very clean design. And companies are going to perceive that as somewhat of a prototype rather than a finished product. So what we did was we went to a display manufacturer and we said, okay, is there a way that we could perhaps shift the polarizers on the top and the bottom displays so that we can allow people to view off-axis imagery better? And in fact, they could, even though they weren't sure they could. Ultimately, they were able to produce a prototype that actually worked. And this is the stereo technology that we're using for CAVE2. So with that, we're going to switch over to EVL. Now, bear in mind that we're only transmitting monoscopic video in this case. Truth be told, we have a stereo camera, and I took it to Africa to shoot for a field biology class, and it got covered in dust, so the CCD is completely useless until I clean it up. And so we're doing everything in mono, so the CAVE is also rendering everything in mono, even though normally it's in stereo. So we're going to switch the screen now to Chicago. And we have Andy Johnson. Andy, why don't you introduce yourself?
Hi there, I'm Andy Johnson. I'm a professor here at the Electronic Visualization Laboratory at UIC. And I'm going to give you a tour of the CAVE. So why don't you come this way?
And so JD, who's our camera operator, is holding a GoPro camera on his chest with a wide-angle, lens, just so it looks kind of more impressive. All right, JD, why don't you step inside?
So this is an application that some of you have probably seen, the LIT. These are the stereo panoramic photos of Luxor. And what's really nice seeing them in CAVE2 is that you do really get full 320-degree view, so you can really just turn around to see the full extent of the panoramas. And the brightness, the contrast, the detail on these pictures is really exquisite. You really get to see a lot of the details of the architecture, and you can really take advantage of what the cameras were able to do in capturing this. You can also see, with the upper and lower panels here, these are the panels that Jason was talking about that we had specially constructed. And that means we can really get close to the screens in this space. We really have a lot of freedom of movement. Since we're using an optical tracking system, we don't have any tethering to the glasses or to the wand. So it's really great to be able to move as much as you want and get as close to the screens as you want without being pushed back by ghosting.
All right, so let's switch over maybe to another application. Switch to what we fondly call party favors because the application looks really pretty, like it's a party. It's science, though, real hard for science. Yes. All right, so Luke actually is controlling it from here. We've got actually a web browser that allows us to control the CAVE remotely if we wanted to.
Or we can run it from our cell phones if we're inside the CAVE. So
That's
I can
true,
reach in my pocket, pop up my phone, and change the apps, which is really incredibly convenient during these kinds of work sessions.
At some point, we should put a password because anybody can actually mess with the demo.
So the application you're going to see here is something that was done in collaboration with someone in our chemistry department and really shows off the tracking. So as JD moves around this gold nanoparticle, you really can see how this works, how he's really free to move around the molecules and see them filling the space if this was 3D, and we had the glasses down. So, it really brings back that full capability of VR for, the chemistry people to be inside their work, to really look and see how these things dock, to see how they interact. And in this case, this is just a standard protein data bank file. So it's basically a standard file format that we can just load into the cave, and then we can either move the cave through the space, or JD can physically walk through the space if he really wants to investigate something. He can duck down, he can look up, he can just move naturally and really investigate this incredibly complex structure, as you can see. You can also see how really bright and colorful this is, which is what's really wondrous about having these LCD panels compared to the original cave. We've got insanely bright reds, we've got great contrast, and everything really pops.
And so, just so you know, the track you can see actually in red at the top. You can see the tracking cameras, and we put the tracker device actually on JD, the cameraman, which is why you're seeing things from his perspective. And so quick point I want to make about the previous scene with Luxor is that you can imagine you can do location scouting in just this glorious view that you could never achieve on a regular desktop monitor. You bring this rig out there, like the Google camera, you stick it in the pole, snaps everything in. You could potentially, if you had the ability to transmit this, transmit it back to the cave, and it is astonishing the realism that you get. I had taken panoramic stereo images in Kenya, and I brought them back, and I showed them to the students who went there, and they all had goosebumps because there was such a strong sensation of actually being there again. All right, so let's move on to something a little more fun, even more fun. And
so while we do this transition, I wanted to give JD a chance to talk about the audio system he's been working on for us.
So essentially, the audio system consists of 20 Genelec speakers in a ring around the top of the cave. We're doing 2D first-order ambisonics, which is written in SuperCollider to implement this, and it essentially makes an easy way for the graphics developers to use a sound API that messages SuperCollider with Open Sound Control or OSC messages, and gives them a really simple way to trigger samples and place them in space. We had some issues, obviously, with a huge room full of glass, so we installed acoustic ceiling tiles and some carpeting to kind of mitigate the waves.
And if you're alone in the space, it is a little odd with the audio, but once we get up to, say, 5 people, the clothing really deadens the sound and makes it a comfortable environment. And then we've taken this up to 25, 30 people even in the cave comfortably, whereas in the original cave, having 5 people was a little tight. And what's really nice is people can sort of form groups and reform. So you have conversations that sort of begin as a group, and then individuals can go off and start studying different parts of the space that we're looking at, and then they'll come back together. And it's really amazing how casually people collaborate in this space. And I think the visuals and the audio are all really, coming together to be a part of that. And it just, really seems like a natural place. It just happens that the walls are active, and there just happens to be, 3D models floating in the space.
And also, we started teaching classes in the space as well. Because the display has such high resolution, we can bring in all the standard media that we normally use for teaching classes, like PowerPoints and images and movies. And we've got these little cute chairs that you put on the floor, these things you take on picnics. And the students just sort of spread out on the floor, and they just glare up at the imagery. It's a really awesome experience.
It's really like having a large number of blackboards around, and kind of takes us back to the war room research that inspired a lot of these kinds of workspaces in the past. It's just now we really have enough resolution that we want to have our meetings here, and we want to have class here, because it's just so easy to put up a lot of information and let people compare and contrast, and get work done more effectively, certainly than on a laptop or a simple screen.
Hey Andy, I'm not sure if it's because Arthur was changed the demo, but it's taking longer to load. So we'll just show this one, and maybe you can just explain what we're seeing here.
So this is some work that one of our students is doing with some bioengineers here and some surgeons. And what they did was they took MRI data from a real patient, and that generated these big veins and arteries that you see. And then the computational side is to try and compute and create the smaller veins and arteries that we don't have the resolution yet in MRI to see, but not just create them visually, but to create them based on the blood flow, so that you get a really accurate model of how oxygen is sent around. And really, if someone has a stroke, if there's a blockage, what is the brain going to do? How is that blood going to be rerouted around? And one of the really interesting things that happened was that the surgeons and the radiologists had seen this same model in 3D on a desktop monitor and thought it was fine. But as soon as they came to the cave, just naturally walking around, they immediately spotted several problems that go, no, the brain really doesn't look like that. And so the people doing the simulation could go back and make a more realistic simulation. But they just couldn't see it before, and it was something that was just incredibly intuitively, easily obvious to see in this mode. So we were really happy about that, because we really do want people doing real work, real science, and getting real value out of this kind of technology.
Cool. All right, so let's walk outside the cave for a second so we can give them all a view of the structure itself. While we're doing that, what we wanted to show you besides this brain was we had one student on his spare time create a full-scale one-to-one model of the Starship Enterprise from the Wrath of Khan. And we wanted to show this so bad to Alvy Ray Smith for having created the Genesis effect, because we're huge fans of that movie. So this is the external structure of the cave. You can see the LCD panels are essentially hung from the cave in racks. Most of the electronics for the LCDs are not on the LCDs themselves. They're actually broken out and run through all these cables to the next room. And this actually allows us to keep the displays a lot cooler than standard displays, because once you have a room like this, you're really concentrating a lot of heat into one space, and you're cooking all the inhabitants, right? We also put a little extra air conditioning too, just to be sure. But as you can see, we're running power and video across all these cables up to the cable tray into the next room, where we have a cluster of 36 computers driving the 72 displays. And the 36 computers are connected to 100 gigabits of bandwidth. In the event that in the future, when we're starting to work with folks who have the ability to render at high capacity, we can stream it to do those kinds of experiments. You can see the subwoofer on the bottom there, the two on each end. I really feel sorry for the people who live below us when we have this thing up. And I think that's just about it for the tour of the cave. Does anyone have any questions that we can answer? For you, for the CineGrid Special, it costs, as far as hardware, it cost about $800,000, funded by National Science Foundation and Department of Energy. All the construction, hey, it's the Enterprise. And if you normally when you're there and you hear the audio's up, you can hear the Star Trek theme. It's really it's like the ultimate geek's wet dream. All right, so sorry. So let's take you outside to show you that in fact it is a scale 1-to-1 scale model of the Enterprise. Oh, we have to turn it back into mono. And I'm not sure we have full time, but if you go down to the deflector dish, that's where the engineering is. You'll see the warp core, and also you'll see this is all one student on his spare time. Arthur Nishimoto. And so anytime he does something crazy like this, we call it the Nishimoto effect. Just
bring Arthur in here.
Yeah, we should bring Arthur in here. So this is, there's the warp core, right there. We can actually, if you scroll down, there it is. So there's the engine room. We can actually bring up the little menu, and we can take you to the transporter room too. And so over time, Arthur, if he gets his PhD, he'll have time. He can finally finish the whole Enterprise and put in all the rooms. Here's it. Yeah, a postdoc. Right. And one of the things we found that's kind of useful for the ambisonic sound is that when we bring up menus in the virtual environment, we place the sound where the menu is. So when it does come, you go, well, where's the menu? Well, you can hear it, so you can just sort of turn and find it. Somebody in the back had a question, I think. Yep. It's for mono, it's about 72 megapixels. In stereo, it's about 35.6 or 36 megapixels. Mm-hmm. And so horizontally, we get full 20/20 based on the distance that you stand roughly in the center of the space. Yep. Yep. We have to move on, right? Thank you. Thanks, guys. Yeah, they have to too.